We're back talking about our last definition for a new quantity, a new angular quantity in chapter 12, angular momentum. All right, so we talked last time and said anytime we have movement, right? Anytime we have movement, whether it's translational or rotational, I have some kinetic energy, right? And we defined what rotational kinetic energy is. Now we need to do the same thing for momentum. Anytime we move, we have momentum, whether it's linear momentum or angular momentum. So strictly, we define L, right? L is going to be our angular momentum. Again, folks, I don't know why we have this letter as our variable, but we have capital L as our angular momentum. We define that to be R cross some linear momentum, P. All right, so this actually gives a broad definition for things that are doing flybys, that are not just rotating, but we can turn linear momentum into angular momentum, especially if something was linear and hits something and then starts to spin. If we think about the magnitude of L, right, we can say that is R, the distance from some pivot, right, times m times v, right, which is our velocity coming in, times sine of phi between our angles, our vectors r and v. So let's actually draw a picture of this. Let's draw a slight picture just to get us started. I have, let's say, my r here, and I'm going to come in with some, some p, right? My p is going to be tangent to my circle here. I'm going to say that I have some r distance from the circle, from the center of the circle of my pivot point. And of course, we want to think about this, right? This is our phi angle. I want to have tip to tip, right? I want r extending up, p extending over. That is the angle between them. In this case, it's 90 degrees, which maximizes a cross product. But we're going to see that that's not always the case. We don't always have to have r and p at a 90-degree angle. So in this case, right, thinking back to the right-hand rule, right, I have r cross p gives me something into the page, right? I'm going to actually have L points into the page here. Points into the page. That means that it's negative, all right? We talk about that as a negative L, right? A negative L. Negative corresponds to clockwise. Counterclockwise is positive. That's just a convention. We said everything follows a right-hand rule, but if we had gone back to the beginning of mathematics and physics and said everything follows the left-hand rule and negatives are now positives, positives are now negatives, we could have said that clockwise is going to be our positive. But that's not how things shook out. Counterclockwise is our positive, clockwise is our negative. So when I think about r cross p, right, that is our strict definition. Now, if I'm very lucky and I talk about a rigid body, right, something rotating around itself, something like back to our candle. Y'all are probably getting sick of seeing this candle. But if I think about the angular momentum of this rotating candle, right, I'm thinking now that it has a moment of inertia, and I can say L is equal to I omega, which means omega actually needs to point in and out as well. I think I'm going to kind of get rid of that for now and just talk about the magnitude of L, just so that way it's nice and straightforward. we can always say, okay, am I rotating, is my angular velocity clockwise or counterclockwise? And that is going to tell us, right, by looking at the direction of our thumb, that's going to tell us the direction of L. And if I think about this rigid body rotation, right, this is rotation about some fixed axis or fixed axle, you know. This corollary, PMV, Li omega, right? It's very, very similar, right? We can actually add this to our quantity list, right at the bottom here. I have a very, very similar one-to-one kind of translation between the two. For linear momentum, I have P equals mv. For angular momentum, I have L equals I omega, right? So that kind of rounds out our list here. Let's go into this just a little bit further, right? We do need to conserve. We need to conserve angular momentum, all right? So if I'm spinning and something comes in and collides with me, I need to conserve angular momentum of that system, of the system of me and that thing that just collided with me. And so just like linear momentum, angular momentum is conserved. I'm not going to get into the nitty-gritty of showing that conservation. I don't think anybody wants to see that, but if you do, take a look in the chapter and talk to me, and we can kind of go through it a little bit more. We need to conserve angular momentum just like we're conserving linear momentum. We need to conserve both in a collision, all right? And so that's actually really key when we change our moment of inertia. I need to also update my angular velocity, right? So and the interesting thing about this is I'm not changing mass per se. Right? We talked about this a little bit in chapter 11, where I'm not really increasing or decreasing mass generally. Right? Generally, in a system, the mass stays constant because you can't just vaporize mass by and large. There are a few cases. You can't just add or destroy mass in the system, right? You still need to account for it. In this case, though, with angular momentum, I can change the mass distribution, right? I can change how mass is distributed around a fixed axle. Maybe, I'm spinning around and I bring my arms in really close. Well, now I've changed where this mass is relative to my fixed point. That's going to change how fast or slow I spin, just to conserve that angular momentum. There's a great demo of this. I'll put a link to a good video showing this demo in the description. But angular momentum also needs to be conserved based on how it points as well. We need to conserve L in all collisions, just like we need it to conserve P in these collisions. Is a long way for me to say that. The last thing I want to do is we talked about back in chapter 11 how we could get force from momentum, right? We said that if I talked about dp dt, right, that actually gave me a force. I can look at the same thing here. What I can say is, what if I have dl dt, right? And I'll continue to use vectors for right now, dl dt, and let's use our strict definition of r cross p for this. So I have now d dt of r cross p. And if I break this up, if I distribute the derivative operator, right, I'm going to have dr dt, right, cross p plus r cross dp dt. I had to use the chain rule there a little bit. And now if I think about this, right, if I think about this, dr dt, well, that's velocity, right? R is a position, right? It's telling me how far away from my axle I am, how fast am I changing that position, right? So I really have v cross p plus r cross dp dt. We just got done saying from chapter 11 that that was my force. So I have now two cross products, v cross p plus r cross f. R cross f, we know that. Let's put that aside for a second. V cross p. V is in p. Right? So the direction of v and the direction of p, momentum, are the same direction. Right? They're the same direction. If they're the same direction, that means the angle between them is 0. Let me quick do a little bit of math here, right? Here's my calculator, right? If I find sine of 0, that gives me 0. So this entire cross product actually goes to 0, right? Because they are parallel, and the cross product is maximized when the angle between vectors is 90 degrees, not 0, right? That whole cross product goes to 0, and I'm left with r cross f. A couple video lectures ago, we said that was tau. So dl dt isn't force anymore. dp dt was force. dl dt is like a rotational force. It's torque. Right? So I don't know. There's something so cool about everything being so self-contained and self-consistent, right? That almost all of our linear expressions can easily be turned into angular expressions just by using the angular quantities of the same, thing, right? The same concept. Torque and force are really very similar concepts, even though they're not exactly the same. I don't know. That's cool, man. It's not only cool, it's beautiful. Like there's some beauty in this. And if you don't see that, if you don't appreciate that, that's okay. That's okay. Yeah, I mean, you're not necessarily all really gunned up for physics. I get that. So anywho, that's where I'm going to leave it on angular momentum. We're going to have to do some problems on this, right? To really get a good feeling for this, we're going to have to do some problems. So that's what we're doing next. And like I said, over the next week or so, I'm really going to try and do some worked examples and put those up for y'all. So this is the big release of the chapter, but keep looking out for those worked example videos that I'll keep uploading. Other than that, I'll see you around here next time.